All right, Josipa, you can start as you like. For anyone who's new, we follow a very informal style that begins with not an introduction. You saw an introduction by email, and we're really happy that Josipa is here to give us a talk today. We're going to invite her to just tell us the way things should work. If you want to be uninterrupted, let us know that, or if you're willing to be interrupted along the way, we can do that. And at the end, we're going to encourage young, academically young people without a PhD or those within a PhD of a year or so to ask the first question or two. And if that doesn't happen right away, we'll just go to a system of having people raise their hands so that it's clear what the order is. But Josipa, please.
Okay, and also telling people that this is going to be recorded, I guess that's okay with everyone. So thank you, Chris, again. So for the ones who join us now, my name is Josipa Majstorovic. I'm a postdoctoral fellow at the Eastern Institute at the University of Grenoble. Currently, I'm associated with the ERC funded project Manifolds of Piero Poli. The team of people within the Manifolds project is working toward a common goal, and that is understanding the spatio-temporal evolution of elastic properties on real faults preceding large earthquakes. So understanding what is happening before a fault is approaching rupture state. My work within the team was to apply machine learning to better constrain low magnitude seismicity before large earthquakes and to understand how we can benefit from machine learning. And in general, the final goal of my project would be to be able to obtain a model, machine learning model that can detect earthquakes in the continuous data, and at the same time extract information about the earthquake position using only one station and using only earthquake waveforms. So how I imagine this talk to be is to give you kind of the pipeline or the overline of what we did in 1 year of work. So how we reached from how we started with the data and ended up with our extended catalog. I will start with the study case. So the main focus is in our case, a licular earthquake that occurred in April 6, 2009, right beneath the city of Aquila. I'm pretty sure that all of you or most of you are familiar with this earthquake. It was quite devastating earthquake that was preceded by 3 months long foreshock sequence and followed by 7 to 8 months long aftershock sequence. But what's interesting, what was interesting for us is to understand, was there something happening, near the fault before this sequence of earthquakes occurred. So if we go to the, if we filter all the events that happened near the fault and go back in time, so up to 1990, we can see that before 2009, reported by INGV catalog, there's only 125 events. So associated with this small region around Aquila station. Around AQ station, which is actually placed close to the fault that was responsible for the licular earthquake. So, if you want to study what happened before and so long back in history, so like 20 years ago, we are faced with the fact that we only can handle or have information about one station, and that is AQ station that was recorded for so long. So faced with the fact that we only had one station and so many data, kind of machine learning was approach that we consider was the best in our case. And if we go back to the state of art, in that point, there was, machine learning was an active study in seismology. But for us, the most interesting studies were done by Perel and collaborators 2018, Lomax and collaborators 2019, and Marini and collaborators 2020. So why? Because these three studies show that just by using earthquake waveforms, they were able to learn a deep learning algorithm, in this case, convolutional neural networks, to perform specific tasks, and that is detection and earthquake location. But when you go back to these studies and you really want to understand why specific model or how this can be applied to continuous data, or how can be this applied to your specific case, you cannot miss lack of information. And that's why we wanted to extend these studies and, carefully explain why we want to use particular model on the continuous data. So in our case, we also decided, motivated by this study, to use convolutional neural networks, which are deep learning supervised algorithm that were initially developed for image classification. So if you would give an image to this algorithm, they would classify this information on this image into certain classes that you would give to your algorithm. They usually consist of several hidden layers, which are divided in two groups: one for feature learning, which consists of convolutional layers, ReLU activation layers, and so on. And then the second part of these hidden layers are the one related to classification itself. So usually consist of fully connected layers and so normalizing functions. So having now our idea in mind, having decided that we are going to use convolutional neural networks, the next step was we needed to build a good database for our future model. So what we asked ourselves in this case was, okay, so we want to use earthquake waveforms, 3 components. So what kind of database I have to have that I would be able to extract really local events, so the events that are happening close to the fault, in this case, close to our station. And throughout this work, I will refer to the local as something that is within 10 kilometers of the station, so the small patch that I showed you earlier. So to answer that question, for us, the reasonable answer was that we need to show our model or possible earthquakes that can model encountering the continuous data. So building a database of events on the existing catalog of earthquakes that contain local, regional, and teleseismic events, and then from this catalog of the earthquakes to search for them in the 30 years of data recorded at the AQ station. So first, we had to build out a catalog of earthquakes. To do that, I used 3 catalogs. The INGV for one for 30 years, a USGS catalog that I downloaded only for magnitude larger than 4.5, just to fill up the gap that INGV didn't have. And very importantly, we also used Valaros and collaborators catalog from 2013 that provided very huge sequence of this earthquake related to 2009 main shock. So these 3, when I merged these 3 catalog, I ended up with 500,000 events that I searched in my seismograms, and using some selection process like asking or wanted to have signal to noise ratio larger than 2, I ended up with 65,000 accepted earthquakes that define my database of events. Some of the other constraints, not only just having signal to noise ratio larger than 2, is also, for example, avoiding to have even within the event of my extracted window. Also, deciding to have this window just 25 seconds long, because in that case we make sure that P and S arrival and coda waves of our local earthquakes would be catched. Then also having all the components present and so on. And so to go further and ask ourselves, so okay, now I should be able to recognize what is a local earthquake from regional teleseismic. Next step is to also have model that can be able to recognize signal from the noise. So we had to prepare a supplementary database that consists of the noise. And in that case, we choose random dates between the earthquakes that we had from our extensive catalog, also 25 seconds traces, try to evenly distribute them per night and day and year and so on. And so here I'm showing you how, so earthquake waveform and a noise waveform looks like, so what I call positive sample and a negative sample. So it's good to know that all these events within my database, I only did trend, normalized by the maximum out of the 3 component, and so no filtering involved in my case. So having my database ready and deciding what deep learning algorithm I'm going to use, next step, and quite difficult one I would say, is how to define a good framework to distinguish local events. And so what I want to say by this is, okay, so we want to have a detector model, but also we want to detect, signal from noise. And then we also want to have some model that can recognize local events, so what we call characterization model. These problems can be solved in 2 different ways. So detection is a simple classification, binary classification, so signal or noise. But the characterization model, you can solve it in a classification way or regression way. In our case, we choose to work only with distance and magnitude as like 2 characteristical labels that can help us the best to identify local events. And we eventually decided to start with the classification, since it looks like simpler problem to solve. Next, defining destruction. So that was the question, whether we want to have a detector and a characterization model as within one model. Do I want to have 2 separated models, or do I even want to have 3 separated models where one model will be for detection, one characterization model for distance classification, and the third characterization model for magnitude classification? Eventually, we went for a 2-stage structure by thinking that, okay, so we are now entering the sphere of the machine learning, how the machine learning model can work better. So our reasoning was that, so for the detector model, we can always build up a balanced data set. So we can always extract as much as noise data as there are earthquake signals. So, but in the characterization model, we are doomed. We were always going to have unbalanced model due to physical processes associated with earthquakes. So we wanted to separate these 2 tasks, so to kind of maybe help detector to be trained better, and then the characterization model. I mean, we are left with what we have. I mean, data are as they are. The third let's say task that we needed to decide on is to how much of these classes per distance and magnitude we really want to. I did several tests that I'm not really showing here, but I mean, further on, I will show you results with these 2 configurations. So eventually we went with something quite, straightforward. Okay, for distance, that was quite important. So having something close to the station, further away. For the magnitude, I mean, magnitude is quite difficult, was quite difficult to solve for, so we tried 2 different results. And the fourth one is basically asking ourselves, is the data set that we build really the best one? So can we some kind of solve or help our model with this balanced and unbalanced question? If increasing the level of SNR is going to improve my model, and also if, for example, completely remove the teleseismic event is help or not help our model to do what we want it to. So just to reiterate, this is how our framework looked like. So we had a two-stage pipeline using 1D convolutional neural networks, where in the first stage, we train a CNN detector that is able to classify between positive and negative samples between earthquakes and signal. And as an output, is giving us a probability whether in the window of question there is a noise, so then it means that probability is close to 0, and whether there is a signal, probability close to 1. And in the next stage, we trained a CNN characterization model, which is only working with positive samples. And as an output, this model is giving us probability whether the signal in question belongs to which class of the distance and magnitude it belongs. So meaning the class that has the maximum probability is the one where this signal belongs. So just to go back to this unbalanced and balanced question, so here I'm showing you the distribution of distance and magnitude for my what I call original dataset. And if if I go further and show you these 3 datasets that we built for trying to solve the problem of the magnitude, because it turns out that the magnitude was much difficult to solve than the distance. So we tried to build up a dataset that has the same number of magnitude samples. And this is what I call the subscript MB. Then compared to my original dataset, I also tried to increase the level of SNR and build up another dataset that I called without subscript RMS. And then the third dataset, the one I told you that I removed teleseismic events, and this is the one with the subscript field. So basically, all this, you can see that all this new dataset, we had suffered by losing some events, but eventually the mean value of the samples within the dataset was larger. So that's something to have in mind. And again, if you look at this distribution, so this is the distribution of this dataset, but per individual group. So this group is, for example, all the events that belong to the epicentral distance close to the station and magnitude having less than 1. And for example, this one is all the events further away from the station, so further than 10 kilometers, but having the magnitude also less than 1. So you can see that I mean, no matter what we do, I mean, the problem is always going to be quite unbalanced when it comes to characterization model. So now when we have, method, database, and the framework, next step is the training, validation, and evaluation. I'm sure that, I mean, you're familiar with the terms here, so I will go quickly here. What we do, we all separated our databases in 3 smaller data sets, so training, validation, evaluation. Training and validation were done one after another. And what we do, we follow the loss function versus epochs when the loss function of validation training sets start to diverge. This is meaning that our model is overfitting, so we stop and just look at the model just before this. Of course, instead of looking at the loss function, we can also follow the accuracy versus epochs. And this is this is what we essentially do. What we tested was basically common parameters within the machine learning community. So there is a you need to define how your CNN architecture will look like, how many convolutional layers you will have, how many fully connected layers. So what we did, we to test only 2 architectures that I will talk a little bit further. Then we test 4 different parameters concerning the training itself. So for the characterization,
Yeah. Oh, it's Chris. I just wonder if you wouldn't mind answering the question. It's about the idea of balanced and unbalanced uh, events. So, you know, the slide, yeah, this slide here, thank you. I mean, I guess part of this is just the frequency magnitude statistics of the events, right? You have a lot more small ones than big ones. So that part is you're never going to get away from, right?
No, never. That's true. I mean, that's the point. That was the point. Yes. So this slide just telling us that, I mean, if there is no way, yes, from getting away from this, and that's why characterization model that I will show you was much difficult to train, and for us was important to, for this purpose, also separate detection and characterization, which was not done before. So just to try to help detector to work better, but then characterization model we have to work with the data we have.
I see. Yeah, thank you.
Yes, so here, just wanted to also comment that we try to test two different CNN architectures, so meaning different number of layers, where the first one that I call deep or 7-layer CNN is based on parallel work, and actually the other two works follow parallel. So this is something that it seems that sticked out in the literature. So we try to test this exact architecture, which was not, have to say, exact completely, just because we need to make some decisions. For example, our input layer was smaller than what they had, so meaning that we had to remove one layer to be able to build up this architecture. But I mean, essentially, this is what they had. And then we also set up this smaller, that I call shallow or 3-layer CNN, which has the less number of layers, but the number of trainable events is the same within the both. And so this is all the parameters that I tested for, and so perturbation of all these parameters gave me 40 tests, and I performed the grid search to find the best combination of all of these different parameters. What I'm going to show you, so I'm going to show you some results of the validation, is this table plots, where basically each test, each rectangular here is associated with a test with the different parameters, so it's kind of easier to compare 48 tests at the same time. And what I'm going to plot here is the maximum scored accuracy for each model associated with so these specific parameters. So results for the CNN detector. I have to emphasize that it was done with my original database. And on the left, you have the validation results in this grid search form. And then on the right, you have the evaluation dataset. So what we can see from this grid search, that detection problem was, I mean, it seems to be easy to solve, because most of these parameters is actually giving us a quite good accuracy. There are a few of this combination where if you choose them from the beginning, you would be stuck. But I mean, eventually, most of them work good. And then if you choose the best out of these 48 associated with these parameters, and then apply it on the evaluation dataset, so the data the model never seen before. Here is the estimated ROC curve, and we can see that it's still doing a pretty good job. Eventually, we decided to put, or to see what is going to be our statistics if we put very high threshold. In this case, 0.99, and this is the resulting confusion matrix. So what's important for us, that by setting this very high threshold, so 0.99, we obtain very good precision, 100 precision, meaning that none of the noise windows were classified as signals. So we were okay by the fact that if we use some signals, meaning that some signals will be classified as noise, but we really didn't want our detector to be contaminated with noise, meaning that some noise is classified as a signal. So we, in our application on the continuous data, we set this very high threshold of 0.99. Next, we have results for the CNN characterization model. So again, this is done with the original data set. The results are with the original data set and with these specific distance and magnitude classes. Again, on the left, you have the validation grid search results. On the right, you have the evaluation results. So what we can see for the validation is that distance problem or task was much easier to solve than the magnitudes. So most of these parameters provide us with tests that would be able to reach very high accuracy value. While for the magnitude, there are some models that didn't learn anything. This was expected. The magnitude class had 4 classes, but still, it's interesting to see. And so if we choose, again, the best model out of these 48 and apply a deviation, this is the final confusion matrix. What was important for us that, again, so the, how to say, we lost some events by having this type of model, because some of our local events were classified as not being local, but not a lot of the region and teleseismic events were classified as local. So that was important for us. For the magnitude situation, as we talked about this balanced and unbalanced things, it's quite messy. But eventually, we obtained the accuracy of 68%, and if we look only at the local events, the accuracy was 73%, so we were happy with that. Here I'm showing you the misclassified events with our CNN characterization model, and you can see that this misclassification is happening on these borders between the classes. So here, the 10 kilometers border, and here for 1, 2, 3, and 4 magnitude. So at this point, when we were discussing this, we realized that it might be interesting to test the regression form instead of classification, and to see, whether we can have something that we can use in the application and can give us more information. Next, here you can see some experiments that are performed, especially for the classification problem. So here you can see that I tested 2 magnitude class versus 4 magnitude class, but also I tried to separate distance and magnitude task. Also, you have different results for different data sets. And here are the parameters that gave the best results, the best models. So the architecture, optimization algorithm, learning rate, moment, and batch. So what you can see here is that there is some certain parameters are actually giving us better results overall. So it seems that the 7-layer CNN architecture is going to work in most cases compared to 3-layer CNN model. If you look at the distance and magnitude accuracy here, you can see for the distance, we were not really able to go above this 92, so from 90 to 92% of accuracy. While the magnitude, you can see that we got the best accuracy with this model that had balanced number of events within each magnitude class. Eventually, when we apply all this best model from this experiment to the evaluation data set, here you can see the results. So on the left, the distance accuracy, on the right, the magnitude accuracy for this. These numbers are associated with numbers here. So eventually we went as a model associated with the experiment 3 as the best one, because the distance accuracy was the best. And for us, I mean, we wanted to do, you know, a better job with the distance task than with the magnitude task. But eventually, you know, even those models like here, that's, you know, was giving us like 10% better accuracy on the evaluation data set. So here it was not doing a good job. Now maybe the most interesting part is applying these two trained CNN models on the continuous data and how we extended our catalog. So here is the output of the CNN detector on the 2 hours of the data. So on the left you have the amplitude, and on the right you have detected the probability in yellow. So you can see how the detector is actually performing. This is obtained by running the 25-second slide window with the 90% overlap on the GPUs. So we can see that setting different thresholds is going to give us different detections, of course. And if we set very high threshold, we are going to really end up with the ones associated with earthquakes, you know, having less false detections. And then for each time step that scored very high probability, we would extract the distance and magnitude class. So here's the zoom in a few of these newly detected events. You can see the detector probability score, and also the distance and magnitude class that they were classified to. So I'm here also showing, for example, events that were classified in the less than 1 magnitude class and 1 to 2 magnitude class. So what is so here with the green lines is this time window where the probability was maximum. So if you imagine like this window within this green lines moving, it means that at one point when there was this signal within these green lines, the probabilities start to rise. And also here you can see, it's interesting that, I mean, the model is seeing something here and something here, but eventually we were able to extract this event, even though, I mean, not really be sure what are these signals here. Okay, maybe the best application or the best performance of our model was to compare the actual detection obtained by our two-stage pipeline with the what was existing before, so with the detection from the pre-existing catalogs. So the main catalog here on the right is these three are the detections from these three catalogs. And on the right, I'm showing you detections from our two-stage pipeline. So this is the February 2009, and I'm showing you only the local events, so only events that were classified close to the station. So you can see that we detect more and more precisely around 270 more detections. It is encouraging that this new seismicity is actually following the old one. So it means that, I mean, the models are doing a good job. I mean, eventually I did check all these detections manually, and they were detections. So, I mean, but you cannot do it for the 20 years of data. So we tested for this small period on the continuous data. Here again, for the same thing, but for February and March with the 600 view detections, you can, if I plot all these events, so each event here in the row is another event, you can see that they are aligned around 100 so around 5 seconds. So basically the same, how to say, the same how my samples look like in my database. That's where my detector gave me the highest probability. That's why they all align at the 5 seconds. And then if we plot the distribution of these events per hour, we can there are more detections during the night, which also makes sense because noise level should be smaller than during the day. And then finally, if we apply our two-stage pipeline on the 30 years of data and extract only local catalog, this is the resulting cumulative sum over the years. So here are several things to note. So it was encouraging that we actually were able to detect this jump in 2009, but also detecting something before 2009. And so here you can see the comparison of so our detections with the, again, main catalog of total before 2009 and for 2009 year. The distribution of magnitude is also making sense, but I mean, we always need to keep in mind that characterization model, especially magnitude task, is biased. What is maybe interesting to emphasize, I obtained all this local catalog in less than 3 hours because it took me 2.5 seconds to scan one day. And then also my data were divided in 4 periods, so it was easy to just simultaneously scan 4 periods of time and obtain all this in less than 3 hours, which is quite remarkable. But there is a big but, and that's that this extended catalog was obtained by some cleaning, so some post-processing, and that's because when we went back to some of this detection in 2004, in 1994, we realized that a lot of these detections were actually gaps. So our model had problem with gaps, and here I'm showing you how one of these detections looked like. Again, you have detector probability on the right and the amplitude on the left, and you can see a gap here and how the probability was highest for this gap here, and also again here for this gap here. So what we think the problem might be coming is the fact that the CNN actually involves several convolution, which is some kind of filtering. So maybe the model itself sees these gaps as filter traces, and since this some kind of resembles earthquake, it might be that that's what confuses the model. You had this it looks like a burst of energy, even though it's just a gap. And so here I'm showing you some of the examples. So it didn't matter if the gap is happening on only one component, on 3 components in different times, on 2 components, or if it's large like this. So at that point, we actually realized that if we want to really have like a 2-stage pipeline that can deal with this kind of problem, we need to do data augmentation, which I will talk a little bit later. So here I'm showing you also something interesting. Again, our CNN catalog is here in blue, but here I'm also plotting you the main catalog. So again, the cumulative sum over the years. And so before I didn't put any threshold on the distance and magnitude probabilities. But if I do that, so if I put the threshold on the distance probability, I still obtain, this jump in 2009 and some detections before. If I do this for magnitude, we can see that in that case, we do not catch all the seismicity that was reported by main catalog. And even so, if I include both thresholds, we lose some of the detections. But again, which is good, have some detections before 2009. And something also what was interesting for me, so I tried to apply two-stage pipeline that was completely trained on a database that was obtained by filtering these teleseismic events and having a slightly larger signal-to-noise ratio, just to see whether these if the model trained on this, let's say, better data set, when I say better, meaning having larger signal-to-noise ratio, would give us better results, or same results. So here again, for the February 2009, only local catalog. In black is the two catalogs, one obtained with the original data set, the other obtained with this FILT database. And in the red is again a main catalog. And you can see that we do detect much more events that were reported before, but not the same number as with the original, as the model trained on the original dataset. So losing around 70 detections. Yes, so with this, I would like to slowly finish with some future perspectives. So based on all this experience that we did at TECTONIC, we realized that we need to do some data augmentation with our model. Also, since there have been some published earthquake databases like STED by Josipa and Kobylartis 2009, which is much larger than our regional database and more variable. So the question would be if, retraining our two-stage pipeline with this dataset would, what would be the results? The third point is, as I already mentioned, trying regression over characterization model for earthquake location. And then maybe, and then the fourth step, maybe the most interesting to me, would be to go further into the CNN black box nature to understand what is happening there, meaning trying to figure out what is the, for example, optimal input in our two models, how the filters look like on different level of CNN model, and which part of the CNN are activated for different positive and negative samples. And the last, some very recent, like 1 week old results for data augmentation. So what I tried is to do is to add some Gaussian noise in my positive negative samples, also to perform some circular shift on the positive samples and to add gaps in my negative samples. And if I do the augmentation in this order and train it on my original data set and test this new model on the difficult examples. So only on the examples where my model, my previous model failed. So all these difficult detection with gaps. You can see the output probability. So now the detector probability, the mean value is around 0.5, which is much better than before, because before all this false detection had a probability larger than 0.99. And if I put 0.99 in this case, I would only have 2 detection out of this 5,000 that I had before. And if I don't, for example, it's interesting, if I don't include noise, this probability histogram is even shifting to smaller mean value. But putting a 0.99 threshold, I got 3 detection out of this 5,000. But so this is encouraging and quite interesting. And with this, I would like to finish my talk. So with some small conclusions. So we successfully trained the CNN model to differentiate between earthquake and noise windows, and also to classify earthquakes based on 2 labels, which is distance and magnitude, using only earthquake waveforms. And we were able, by using this 2-stage pipeline, to detect new events in our continuous data from only 1 station and successfully label them as local earthquakes. And just small comments. So designing a CNN model or any deep learning algorithm, in my opinion, or any applicable pipeline is highly customizable process. And now we can also discuss, if this is good or bad. I would say it's good because it means that it can be applied to many different problems and tasks. But again, it's bad because it's difficult to, compare all these models eventually. And yes, thank you for the attention.
Very nice. Everyone, please unmute. Really interesting. Thanks so much, Josipa. Do we have a student or a postdoc who'd like to start things off with questions? And for everyone else, please use the raise hand feature maybe. Laura, please ask, and then we'll go to Chuck Ammon.
Yeah, thank you. It's a quick question about the metrics. What metrics did you use during the training phase?
What metrics?
Yeah.
I'm not sure if I understand what the metrics represents.
During the training phase, I guess cross entropy.
Ah, you mean what was the final loss function that I used?
Yeah.
So for the binary, for the both problems, I used the binary with loss logits from PyTorch. Yes, so all this algorithm is implemented in PyTorch. So compared to what they done in TensorFlow and no PyTorch packages.
Okay.
Yeah.
So then cross entropy, yeah.
Yes, it's a binary cross entropy with logits. I don't know if that's answer your question. Like
Yeah.
this specific
Okay,
function that I used.
Yeah, okay. Thank you.
Welcome.
Great. Chuck Ammon, go ahead. And then anyone else, please jump in.
If I understood correctly, it seemed to work really well, or all the different methods you tried seemed to work really well with distance. I wonder if you use more distance classifications, or I think of them as bins, than just a closer than 10, farther than 10, if that might then back up and help the magnitude classifications, because that kind of information seems to be important in terms of looking at the signal, knowing how far away it is, and estimating the magnitude. But I could be completely off base because I don't understand all the details.
Yeah, no, but that's a good question. I did try, several of these different classes combination, and I must admit I don't remember by heart now, the results. But our general feeling was that it seems that the number of classes between distance and magnitude was not helping each other to solve the problem. So for example, here you can see that distance with two classes compared to I don't have, no, sorry, I cannot show you this here, but general opinion was that it's not helping if I have three classes of the distance, that it's going to help the magnitude classification somehow. And that's why we went to this simple configuration of just having, close to the station, further away from the station, because in that case, we were able to train model better just having two classes for a classification to solve. And the magnitude is just, yes, difficult.
Thank you.
Yes.
Josipa, it's Chris. I have a question connected to the time window that you took, because I can kind of imagine that, especially for small events, 25 seconds is kind of a long time. Did you try different shorter time windows?
Yeah, I would. My general opinion is that a different window would give different results. We choose 25 seconds. We thought that that would, give us enough. Yeah, but that's the question now. We wanted to be sure that to have PNS where arrival and code away of larger earthquakes, close to the station, and smaller. You have to compensate since. Eventually, yes, you are solving, the problem for small magnitude and for longer magnitude. So I didn't try a different window because we thought that this could be, be the best for our application. Maybe, as you say, maybe doing smaller window, but I don't know, I'm not sure. Like, what would you suggest, like, for this? Like, in your point of view, what do you think would be?
No, I don't have a good, kind of any kind of magic answer at all. I'm just thinking 25 seconds sounds like it includes a lot of noise. So then it makes it potentially more difficult to train, I suppose,
Yes, but I mean, if I took smaller window than that, I don't know. Yeah, you wouldn't have, I think, code. I don't know. Yes. Yeah. I don't know if that would be good. I didn't try different window. So.
Gotcha. Thank you. Chris Johnson, please go ahead.
Hi, Josipa. This is kind of a follow-up with what Chris just asked. In your model design, you followed the Lomax and then the I forget the one that starts with a P, either way. So one thing, did you test is the filter width size? Because this is going to kind of address what Chris was asking. So if you're narrowing that filter width, then you're kind of focusing where you're trying to find energy in the waveforms. Did you test that part of the model design?
Yeah, I mean, that's a good question. We are actually testing it now. So the problem is that, yes, maybe didn't emphasize enough. There are so many things that you can test, and we decide that maybe the kernel size within the convolution layers should be something tested, because we used the 3-size kernel size, but I think, yes, the maybe larger one might work better. So we are basically testing this now.
Right. And just a comment, I've worked with gaps in the data similar to what you, and I found that Gaussian noise does not solve that problem.
Yeah.
And more of a building a synthetic random walk style noise that mimics this. You have to extracting all the properties from the waveforms and building it that way is what I've found to work best. But that's actually very tedious to do. So just a comment on you're not alone struggling with that problem.
That's good. Yeah, I was just thinking the other day that like adding a random noise, I don't think if I really want to do that, because if I'm doing this, I must be really masking the events, smaller events that I really want to detect. So I did try something very simple. Yes, just adding, like a standard deviation of the trace. So my standard deviation, the noise was the standard deviation of my trace. But what if this would really mask my smaller events and then just really give the model something so difficult to solve that? I mean, what's the point? I mean, maybe it's also a question, I don't know what you think, whether the CNN is learning a noise function associated with a small magnitude events, because it's going to see, small events for this specific small patch on the same station. Is there but that's the question, is there some kind of mean and start deviation at the noise at the station so that we can use this information and not, I don't know. Yeah, I'm not sure if I'm going there with something with this, but I agree that just must be very careful when adding Gaussian noise. Thank you for a comment. That's encouraging.
Oh, thank you.
Other questions? People who are here?
Hey, I have a question. This is Eliza.
Hello.
Hi. You were saying that there's a lot less noise at night, which makes sense. And I'm wondering if you looked at data that's just in the last 12 months, because there's so much less cultural noise given all the lockdowns, if your detections would be better for recent data too, or if you've thought about that.
Actually, I didn't. That's a good idea. I could have done. Yeah, I could like I can use this Corona situation for something. Yeah. Yeah, I should do that, because then I never thought about that. I mean, we just focused on this and then didn't scan it further than 2019. So okay, yeah, thanks.
You made believers out of everyone, it looks like. But...
Yeah. Maybe I was too fast.
Thomas King, no mic here. Sorry, very interesting work. I missed the rest of it. Do you see it, Josipa? Why did you choose a CNN over a recurrent neural network, such as a time delay neural network? Maybe do you see the chat?
Yeah. Yes. Should I read the Should I read the question aloud?
Everyone can read it. Everyone can read it. I'm sure. Yeah. But maybe just he says he has no mic, but apparently he can hear you, so you can just answer.
Yes. Okay. It's a very simple answer to that question. We were motivated by these 3 works that I showed you. That I showed that things were working at some degree, and then we choose the classification over regression. Just out of the simplicity. I mean, I must say that I'm 1 year in this machine learning. I didn't do this before, so for me it seems like an easier problem to solve. But it doesn't seem so. Maybe so. Yeah, that's just maybe lack of my knowledge at that point 1 year ago. But yes, now it might be interesting to test. When I have all this. Framework, like changing something, and I have something to compare to now. So that's why I appreciate like the ideas that might work. Thank you, Thomas.
Hi, Chris. Can I ask a question?
Please.
David, yes. Hi, Josipa. I'm wondering, when you were showing your time series, so you mentioned that you actually found a lot of activity before the main shock that wasn't known. But then in terms of aftershocks, you found more aftershocks, obviously, but I mean, the increase is not as strong, if I'm correct. Yeah. And can you show the first time series we were showing actually beforehand? Yes, this one. Thank you.
This one?
No, this one. Yeah, exactly this one. Yeah, because well, you clearly can see an acceleration before the main shock, so a long-term acceleration, and then which I don't know. Well, first question: do you think it's real or it's related to your data selection or your processing? And the second question, and then the aftershock rate seems to be very constant very quickly, and stays constant for years, but with a rate that is relatively strong compared to the pre-main shock rate. So again, is this something real, you think, or related to your processing?
Yeah, so related to these detections, I mean, I wouldn't, there's expression, I wouldn't put my hand into fire that this is the way it is. We still have to be, sure. We still need to do some tests, especially because we found out that the gaps were in the data, and especially. I mean, I don't have a catalog with the gaps here, so I cannot show you that some of the periods were showing the increase. And then if we zoom there and look at this detection, it turns out to be the gaps. Now I'm pretty sure they are not the gaps, but I don't know, like, I didn't really, what we tried is we used very small, we put this threshold on distance and magnitude, very high threshold, and we try to do the the correlation between all these events, And what we found is that nothing was happening actually before 2009. But this is everything we need to check. So I cannot really tell you that it is how it is. So, but now we are working with this catalog. So now it's all these questions. Yes, we need to. I didn't really honestly have time to go through all these detections yet. There are a lot of them, and we were kind of surprised by these gaps. I mean, it's normal, but so we are now working with this, making model work good with the things we know that failed, and then we will scan again. So actually, I'm planning to scan this again to see if I will get the same rates of the seismicity. So I'm sorry I don't have this information now.
Josipa, while we're waiting for other people to think of questions if they'd like to, I'm curious, okay, so you wanted to develop this for one station, but is there a reason not to go to another station, to include two stations? It feels like this would really help in terms of magnitude, for example.
Yeah, but then you are asking yourselves, I guess there will be seismologists telling me, I mean, probably there is a technique, better than to do. There are other techniques that work better with two stations, And the main idea behind all of this was really to go back in time, and there you don't have, stations. As far as we know, as I know, there was only AQU station recording so back 20 years of time. So this was motivated really with our kind of idea to have the algorithm to scan this back in time. So having only one station in that case. But yeah, I would be interesting to include another, instead having 3 component, but having 6 component, for example, for 2 stations, and see how it's going to work, just out of the curiosity. But I don't know if people will tell me, well, there are better algorithms to work with 2 stations. So that's the thing.
Yeah.
One of the idea that I didn't mention that was also to use this model that is now applied on, tested, applied on this one region, and switch to another region, and just apply it on this new region with only one station, compare it with the catalog associated with this small region, and see how it going to performs, and then do some transfer learning. So basically, if based on the results, but I don't know how to answer that question. I don't know if it will work better or not. But if it doesn't work, if it works good, then great. But if it's not, then do some transfer learning using the model we have here. So that's also something interesting. What is good here that we really use only the waveforms from this small region. Most of the detectors that you have now in the literature, they use worldwide events. So we now have this tool or these results, and we can kind of expand. We can compare, if this was better, if this is better, or it's better when we include really worldwide events, or so many things to do.
Yes, thank you. Others? You've done such a good job of convincing everyone that people are.
All right, that was just too fast. Yeah, it's difficult to say, speaking.
Sorry.
Yeah.
Hi, that was a great presentation. Thank you. I had a question, I guess, going back to what you were just talking about with Chris with respect to transfer learning. So if you tried to apply this algorithm somewhere else and it didn't work, what would you try to change inside of the framework? What variables do you think you would look at first? I don't know if variable is the right word, but
yeah,
what would you look at first, I think, to try to I guess, fix it?
Yeah, so what I would do, so basically the steps that I had in mind is like, okay, I apply my algorithm with a new region, new station. I obtain detections and I compare with the catalog there. And then if I see that I'm doing a good job, I mean, that's, you know, perfect. But if I see I'm doing a bad job, then I would take, I would build a new data set from this region. And I would basically do first step, just training. So this 48 grid search, transfer learning plus grid search using this new database to see if I, you know, just by having what I have, but with a new event adding and with the model that I had. So it means that my model is not randomly initialized, but it already has some, you know, weights to work with. Does this going to help? But then the question is, yes, further than that, I'm not sure. I don't know.
Cool, thank you.
Yeah, welcome.
Others? You know, David Marston asked an interesting question about the rates here on this plot that we're looking at. And yeah, I wonder, do you suppose there's some, let's say, changes in velocity structure or attenuation characteristics associated with the earthquake that impact the way you identify things after the event?
I don't know. I don't know. I really didn't. Yes, didn't think about this. Not yet. The only thing we tried is this trying to see if there is really some correlation between these events, but didn't go any further in this. Yeah, I mean, if you have suggestions, what could be, you know, done, I am very happy to hear. You know. That's, you know, this is a lot of, I mean, it's a lot of, maybe it's not a lot, I mean, but for me, it seems like a lot of detections to really go visually and check all of them. So I really want to do some tests and be sure that what I'm seeing is really, you know, events. It was easy to test on few, I mean, I did test on a few like smaller, like 2 months, you know, but 30 years of data, I don't know. Yeah. Have to, because this is, yeah, I mean, dealing with something new. One of the idea was also to just, I don't know. Actually, I'm not sure. Yeah.
Yes, I certainly don't have any magic bullet answers. I suppose one simple thing you could do would be to, you know, pull some equivalent magnitudes and just compare the spectra from before and after. Because
Okay.
maybe the attenuation is different. I don't know. Yeah. Yeah.
Okay. Yeah.
Yeah.
Yes,
Joan.
John.
Joan,
So
please.
Eliza raised an interesting point about the noise characteristics changing with time. And certainly as you go farther and farther back in time, one would expect that as populations grow and so on, and I don't know about this specific area, that the noise, so to what extent might these curves, these rates be affected by changing noise over time?
Yes, I mean, it could be, but I mean, the thing, yeah, what I try to do when I sample noise, I really try to have like a evenly sampling the negative samples evenly in time, in years, just to try to, you know, kind of help maybe avoid this problem. But yes, definitely, I need to be aware that, I mean, for example, most of the positive samples in my data set are really coming from this Valoroso catalog that is associated with 2009 year. So, you know, all the noise associated with my positive samples is kind of, I mean, modern, no, it's around 2009. But my noise, it has samples from before. So yes, I don't know how I can test that, honestly. Now, like out of the blue, I don't know. Yeah, how I can test if the noise is actually affecting the result. Yeah, I'm not sure. What was my idea when I was talking about adding a noise into like a data augmentation was to estimate like a mean and standard deviation of the noise associated with my positive samples. So to be sure that if I'm adding a noise, I'm not going over some standard deviation of the noise of my small magnitude events. But yeah, that's the only idea that I had so far. Thanks.
Other points, questions, comments?
Yes, and Claudio, can you hear me?
Yes.
Yeah. So maybe I have a comment about noise. So the station is located in downtown L'Aquila, so you should expect that the noise changed between before and after the earthquakes, but the 2009 earthquake. But I'm not sure that it's changing in a way that is really easy to predict. I mean, before the earthquake, the city was very busy and crowded, and there is a lot of usual business. But after that, there is a lot of reconstruction. So it started very hard work, and so even also the noise should be very high too. So it's really, I don't think this could be very easy to test and understand. The other point is the bump that we observed after 2016. This is associated with the Norcia earthquake in the north, probably. I don't know if these are earthquakes that really are occurring on a distance less than 10 kilometers or not on L'Aquila. I mean, and so maybe you can check this eventual burst here and change your rate, because it seems to be really associated with the Norcia event. I'm not sure.
But I mean, that means that.
So.
But that means that these Norcia earthquakes, I mean, they should have been in the catalog already, right? I mean.
Yeah, sure.
So I mean, when I did this, yes, you are right. Okay. No, actually, what I can do is basically do what okay. So what I did is comparing the time. So if I have the catalog, if I have an event in the catalog, I would search whether my detection is within the some time of this event in the catalog, and so meaning that if I have the match, I remove this from my catalog. If I'm.
Oh. Yeah, okay. Thanks.
Welcome.
I'm not sure about the comment on the noise, if it can be of some help. I don't know.
Yeah.
If you are interested, we can discuss this later.
Okay, thank you. Yes, I'm interested. I mean, I understand, yes, that AQ station is in a quite busy place. What I understand. So, if all the positive samples that I'm using are happening really after this construction started, then they should be quite contaminated by noise.
Yeah, maybe it's better to check. Yeah.
Yeah, I understand. Thank you.
Thanks.
Ellie, go ahead.
Sorry, I just had another quick question. Is there a reason why you are only looking at epicentral distance instead of hypocentral distance?
No. I mean, it was just a choice that we did. Like, I compared also what I did before and like what looked for us to be, you know, easiest, because if I where is that? Sorry. Yeah. I don't know. Yes, hypocentral distance. In that case, yeah, I don't know, like, if would that work better or not, like, honestly. It was just a choice, not a particular reason, you know?
Mm-hmm.
Yeah.
Thanks.
Welcome, sorry.
Other questions? Comments? And if not, I'm going to ask, please unmute long enough to say thank you to Josipa for a great talk. Really,
Thank you.
really stimulating, very, very nicely done too, Josipa.
Thank you very much.
Yeah, so we have Lisa Tinti talking next week, and with the magic of Manandrine, we're going to have this recording posted so you can check it all out again. Thanks so much, Josipa.
Yes, it was nice meeting you all. Yeah, have a nice day, and thank you again for the invitation. Bye.
Thank you. Thank you. Bye-bye.